This is a brain, and this is a model of the skull, and that layer in between is the dura. From day one, we've been working towards making our surgery faster and less invasive. Preserving the dura, instead of removing it, is a massive leap in that direction.
In May of 2026, as part of our ongoing clinical trials, we performed the very first transdural Neuralink surgery alongside Dr. Lozano at UHN in Toronto, Canada. It's the most cutting-edge version of this surgery that we've yet performed.
The dura is the outermost layer of the brain. It's right beneath the skull, and it's this tough, leather-like protective material that surrounds the brain.
The standard Neuralink surgery thus far has involved opening the dura and removing a portion of that lining so that we can see the brain directly and insert electrodes into its surface. This new version of the surgery skips that step entirely, and our robotic insertion device is able to insert electrode threads directly through the dura into the brain itself.
This is an important step because it makes the surgery safer, less invasive, faster, and potentially allows us to scale the operation to a greater population.
The primary engineering challenges have been, how do you insert threads through the dura mechanically? And then how do you see through the dura such that we can insert threads while avoiding vasculature? The dura is a very tough, leathery layer. Our original needle design was not able to reliably penetrate it. One of the things we did was increase the diameter of our needle just slightly to be able to put our electrodes through the dura.
Distance to the cortical surface. To overcome the first challenge, the blood vision of the blood vessels, we used ICG video angiography. ICG is the dye that can be injected through a vein, and then used infrared light to see the blood vessels glowing right through the dura, so the robot could steer threads safely around them. Second, to know how deep, we used an optical system called optical coherence tomography to determine the distance of the cortical surface from the dural surface. This is the OCT portion of the robot. So you see the laser, optics, and the robot head module here. So the laser light goes through this optics and then delivered to the robot head through this fiber. The light coming back from the brain is coupled into this lens and then coupled into this fiber. So the light is delivered through this fiber optics again and then processed and then visualized as a 3D volume of the brain tomography. This is the brain proxy that we used to test our OCT system. So it has multiple layers of membrane that mimics the human brain anatomy and the brain motion. On the screen, what you're seeing is thin dural layer and SAS, subarachnoid space under the dura, and then the cortex. So as you see here, the distance from the dural surface to the cortex is actively changing in the live human. OCT allows us to measure the distance from the top of the dura to the cortex with high accuracy, so we can insert our threads into the cortex with high precision.
Part of the mission in helping as many people as possible is being able to do as many surgeries as possible. And one way to do as many surgeries as possible is having robots do the procedure with clinical supervision. The step prior to automating surgery and bringing in robotics is thinking about what steps can you delete such that you don't even need a robot to do it. The transdural procedure was our way of deleting the directomy step completely to make the surgery faster, simpler, safer, to be able to expand what's possible and to help even more people with unmet medical needs.